You are listening to Data Unleashed, MongoDB and the power of NoSQL applications. Like and subscribe to keep up to date on our latest audiobooks. Data Unleashed, MongoDB and the power of NoSQL applications. Chapter 1, The Data Dilemma, Why Databases Had to Evolve. 1.1 Introduction, The Data Explosion. Take a moment to consider your day so far. Perhaps you checked the weather on your phone, ordered a coffee through an app, or glanced at your smartwatch to see how many steps you've taken. Every single one of these seemingly simple actions generates data. When you scroll through a social media feed, stream a video, or even adjust your smart home thermostat, you are participating in an unprecedented global data explosion. We live in a world awash with information. Data is being created at an astonishing speed, more in a single day than in entire decades just a few generations ago. And it's not just the sheer volume that's remarkable, it's the sheer variety. We're no longer just dealing with neatly organized numbers and text. Today's data includes images, videos, audio recordings, sensor readings from countless devices, social media posts, intricate network logs, and so much more. This deluge of diverse information, generated by billions of interconnected devices and human interactions, has pushed the limits of traditional information systems. It's like trying to manage all the constantly updating content on the entire internet with the tools designed for a single, perfectly sorted library. The old ways, while once revolutionary, simply weren't built for this scale and variety. 1.2 The Reign of Relational Databases, SQL. For more than 3 decades, one type of database reigned supreme, the relational database. If you've heard the term SQL, a reference to the structured query language used to manage them, you're familiar with this powerful and pervasive technology. Relational databases store information in a highly structured way, organizing data into tables with predefined rows and columns, much like a very precise spreadsheet. Each column has a specific name and type, ensuring consistency down to the smallest detail. Their enduring popularity stems from their remarkable ability to maintain data integrity and consistency. This is often summarized by the acronym ACID, atomicity. This means that every database transaction is treated as a single, indivisible unit. If any part of the operation fails, the entire transaction is rolled back, ensuring the database remains in a consistent state. Think of transferring money between bank accounts. The deduction from one account and the addition to another must both happen or neither happens. Consistency. Relational databases enforce strict rules for data validity. Any data written to the database must comply with all defined rules and constraints, ensuring that the database remains correct and reliable. Isolation. This ensures that multiple transactions can occur simultaneously without interfering with each other. Each transaction appears to be executed in isolation, preventing data corruption from concurrent operations. Durability. Once a transaction is committed, the changes are permanent and will survive even in the event of a system failure, such as a power outage. These ACID properties made relational databases the gold standard for applications where data accuracy and reliability were paramount, such as financial systems, inventory management, and traditional business applications. The system was designed to protect your data with meticulous care. 1.3 The Cracks in the Castle, Limitations of SQL in a Modern World. While relational databases excelled at managing structured, consistently formatted data, the demands of the internet age began to expose their inherent limitations. The very strengths that made them popular started to become bottlenecks. One of the biggest challenges arose from scalability. Traditional relational databases typically scale vertically. This means that to handle more users or more data, you essentially buy a bigger, more powerful server with more processing power, memory, and storage. While effective to a point, this approach eventually becomes prohibitively expensive, and there's a physical limit to how large a single server can get. Imagine trying to serve breakfast to a rapidly growing city by building ever larger, more complex single restaurants. Eventually, you run out of space, resources, and it just becomes too unwieldy. The modern internet, however, demanded the ability to scale horizontally, distributing workload across many smaller, cheaper servers. This was a concept relational databases struggled with due to their tightly interconnected table structures. Another significant hurdle was schema rigidity. Before you can store any data in a relational database, you must define a precise blueprint, or schema, for every table. If your application needed to evolve rapidly, perhaps adding a new feature that required a new field for a user, like preferred notification method, you might have to alter the entire database schema. This often involved complex, time-consuming operations that could require taking the database offline, an unacceptable prospect for always-on web applications. It's like trying to frequently re-architect a massive building while people are living in it, versus building with very flexible, modular components. Furthermore, relational databases were primarily optimized for structured, tabular data. They struggled to efficiently handle the diverse and often unstructured data pouring in from web applications, mobile devices, and sensors. Storing things like social media posts, photos, or complex product catalogs with wildly varying attributes often required awkward designarons that sacrificed performance and simplicity. Finally, while robust, performance could suffer, especially in high-traffic, distributed environments. Combining data from multiple tables, a process called joining, across different servers could be computationally intensive, slowing down applications that needed rapid responses. Early internet pioneers, like the teams behind eBay and Dig, famously encountered these database bottlenecks as their user bases exploded, forcing them to find creative, often unconventional, solutions to keep their services running. 1.4 The call for change, introducing the NoSQL movement. Faced with these mounting challenges, visionary engineers at companies like Google and Amazon, who were building applications on an unprecedented scale, began to develop new database technologies tailored to their specific needs. They realized that a single, rigid database model couldn't effectively serve all purposes anymore. What emerged from these innovations was a collective movement known as NoSQL. The term NoSQL stands for not only SQL, rather than no SQL at all. It represents a fundamental departure from the one-size-fits-all approach of traditional relational databases. Instead of insisting on rigid schemas and complex joins for every piece of data, NoSQL embraced a philosophy of diverse database models, each optimized for specific types of data and access patterns. This movement emphasized distributed systems, the ability to spread data and processing across many servers, allowing for massive horizontal scalability. Schema flexibility, the freedom to evolve data structures quickly without cumbersome schema migrations, supporting agile development. High performance, solutions optimized for specific workloads, offering blazing speed for certain types of data operations, even at immense scale. The NoSQL movement wasn't about completely replacing relational databases. It was about providing powerful alternatives, complementing existing solutions, and giving developers and architects the right tools to build the incredibly complex and dynamic applications demanded by the modern internet. It ushered in an era where specialization became key, and the search began for the perfect tool for each unique data challenge. Chapter 2, Beyond Tables, What is NoSQL? 2.1 Unpacking NoSQL. More than just NoSQL. When you first hear NoSQL, it's easy to assume it means a complete rejection of everything SQL databases represent. In reality, the term is better understood as not only SQL. It's a recognition that while SQL databases are incredibly powerful and suited for many tasks, the explosion of new data types, the demand for infinite scalability, and the need for agile development cycles have created scenarios where a different approach isn't just an option, but a necessity. Imagine that traditional SQL databases are like highly organized, specialized filing cabinets. Each drawer is a table, each folder in a drawer is a row, and every document in a folder must fit into a predefined set of slots, columns. This system excels at keeping things meticulously tidy and ensuring every piece of information has its exact, proper place. NoSQL, on the other hand, is not a single, monolithic system. Instead, it's a diverse collection of different database approaches, each designed to solve specific challenges that the filing cabinet model might struggle with. They're like a collection of different types of creative storage solutions. Some are like open-ended portfolios for flexible documents. Others like massive, fast-access warehouses for huge amounts of simple data, and some like intricate mind maps for complex relationships. The key is that they all abandon the rigid table structure, opting for flexibility, massive scale, and specialized performance. 2.2 The 4 Pillars of NoSQL. Different approaches to data. While NoSQL is a broad umbrella, most NoSQL databases fall into one of 4 general categories, each optimized for different data models and use cases. Key value stores. These are the simplest NoSQL databases. Think of them like a giant dictionary or a digital hash map. You store data associated with a unique key, and you retrieve that data by providing the key. There's no complex querying beyond retrieving a value by its key. How they work. Data is stored as a collection of key-value pairs. The key is unique and acts as an identifier, while the value can be anything from a simple string to a complex binary object. Strengths: extremely fast for retrieving data when you know the key, highly scalable for massive datasets, and very simple to use. Practical use: ideal for caching frequently accessed data, like user sessions on a website, shopping cart contents, or simple data that needs to be accessed by a unique identifier. Column family stores. These databases are designed for very large datasets that often have sparse data, meaning not every record has every piece of information, and high write throughput. They organize data into rows and dynamic, column families and columns, allowing for flexible schema evolution. How they work. Think of them as a two-dimensional map. Data is stored in rows, and within each row, columns are grouped into column families. You can add new columns to a row at any time without affecting other rows. Strengths: excellent for handling massive amounts of data, very high write performance, and flexible column structures allow for diverse and evolving data. Practical use: popular for managing time series data, e.g., sensor readings from IoT devices, large-scale analytics, distributed logging, or applications that need to handle millions of writes per second across many servers. Graph databases. Unlike the other types, graph databases don't focus on individual data points, but on the relationships between them. They store data in structures that resemble a graph, consisting of nodes, entities, and edges, relationships between entities. How they work. Nodes represent entities like a person, a place, or a product, and edges represent the relationships between them, e.g., knows, likes, lives in, purchased. Both nodes and edges can have properties attributes. Strengths: incredibly powerful for traversing and querying complex relationships, excellent for recommendations, social networks, and fraud detection. Practical use: building social graphs, who is connected to whom, recommendation engines, people who bought this also bought that, knowledge graphs, and complex dependency mapping. Document databases. This category is our primary focus, as it's where MongoDB truly shines. Document databases store data in flexible, self-contained units called documents. These documents typically use a format similar to JSON, JavaScript object notation, making them highly intuitive for developers. How they work. Each document can contain all the information related to a single entity, much like a digital file or record. Documents can have varying structures, allowing for schema flexibility. They can also contain nested documents or arrays, representing rich, hierarchical data. Strengths: highly flexible schema, natural mapping to object-oriented programming languages, excellent for evolving applications, and strong support for complex queries on semi-structured data. Practical use: user profiles, e-commerce product catalogs, content management systems, mobile app backends, and scenarios where data models are subject to frequent change. Each NoSQL type excels in different scenarios, offering tailored advantages over a one-size-fits-all relational approach. The choice of which NoSQL database to use depends on the specific problem you're trying to solve. 2.3 Core NoSQL Principles: what they offer. Despite their differences, NoSQL databases share several common principles that distinguish them from their relational counterparts and make them attractive for modern applications. Schema flexibility. This is perhaps the most defining characteristic. Unlike relational databases that enforce a strict schema before data is stored, many NoSQL databases allow for a more dynamic, evolving schema. You can add new fields to documents or records without having to modify the entire database structure, which speeds up development and allows applications to adapt quickly to changing business requirements. We'll delve deeper into this concept as schema on read versus schema on write. Horizontal scalability. This is a cornerstone. Instead of relying on one huge, expensive server, NoSQL databases are designed to distribute data and workload across many commodity servers. This scaling out allows for virtually limitless growth, handling massive data volumes and supporting huge numbers of concurrent users by simply adding more servers to the cluster. High performance. Many NoSQL databases prioritize performance for specific workloads. By optimizing their internal structure for certain types of operations, e.g., fast writes, fast key-value lookups, or efficient document retrieval, they can deliver incredible speed for the tasks they are designed for. This often involves techniques like denormalization, storing related data together, even if it means some redundancy, to minimize costly join operations. High availability. Modern applications cannot afford downtime. NoSQL databases are typically built with high availability in mind, meaning they are designed to remain operational even if individual servers fail. Data is often replicated across multiple machines, ensuring that a backup copy is always available to take over if a primary server goes offline, providing continuous service. Relaxed consistency, base versus ACID. While SQL databases champion ACID properties, some NoSQL databases embrace a different set of principles known as base, basically available, soft state, eventually consistent. This is a trade-off. It means that for certain types of applications, the database prioritizes being always available and highly scalable over guaranteeing immediate, absolute consistency across all copies of data at every microsecond. While a new piece of data might not appear instantly everywhere, it will eventually propagate. This model is perfectly acceptable for many web-scale applications where immediate consistency is less critical than continuous uptime, e.g., social media likes. IoT sensor readings might be eventually consistent. It's important to note that MongoDB, while being a NoSQL database, offers strong consistency within a replica set, bridging some of these historical trade-offs to meet more enterprise requirements. Imagine a new shipping company that doesn't just use one kind of truck, like SQL. Instead, it has drones for small, urgent packages, cargo ships for massive international freight, and custom delivery vans for daily routes. Each is optimized for its task, allowing the company to handle a vast array of shipping needs efficiently. 2.4. Choosing the right tool. When and where NoSQL shines. It's crucial to understand that NoSQL databases aren't a universal replacement for SQL. Relational databases still excel at managing highly structured, transactional data that requires strict ACID guarantees, like financial ledgers or systems of record. However, NoSQL databases truly shine in environments characterized by rapidly changing data requirements. Startups and agile development teams often pivot quickly, adding new features that drastically alter data models. NoSQL's flexible schema allows for this without painful database migrations. Massive data volumes and high traffic. When you're dealing with petabytes of data or millions of users interacting simultaneously, like a global social media platform or an IoT network, horizontal scalability is non-negotiable. Need for continuous availability. E-commerce sites, streaming services, and mobile applications simply cannot afford downtime. NoSQL's built-in replication and distributed architectures ensure that services remain online. Diverse data types. When your application handles a mix of structured user profiles, semi-structured sensor readings, and unstructured media files, a flexible document model can accommodate it all naturally. This chapter sets the stage. Now that we understand why NoSQL emerged and the different forms it takes, we can zoom in on the document database model and one of its most prominent implementations, MongoDB. Chapter 3, The Document Database, a Revolution in Data Modeling. 3.1, What is a document database? Among the diverse landscape of NoSQL databases, the document database stands out for its intuitive and flexible approach to data storage. At its core, a document database stores data in self-contained units called documents. Unlike the rigid rows in a relational table that must conform to a predefined set of columns, a document can be a complete, independent record about a single entity. It's flexible, different documents within the same collection can even have different fields. To grasp this concept, imagine a digital folder. Inside this folder, you could put everything related to a single subject, say, a customer. This isn't just one type of form or paper. It might include their name, address, contact details, a list of their recent purchases, their preferred communication methods, and even their saved payment information. Every piece of related information for that customer is in one place, easily accessible and manageable within that folder. This document approach allows for self-contained records. Each document typically holds all the information pertaining to one item or entity, minimizing the need to combine data from multiple sources. Hierarchical structure. Documents can contain nested documents or arrays, allowing for complex, richly structured data that mirrors real-world objects. Flexibility. As we'll explore, the structure of documents can evolve over time without requiring a complete redesign of the database. 3.2. The power of JSON and BSON. The standard format for documents in most document databases, including MongoDB, is based on JSON, JavaScript Object Notation. JSON is a lightweight, human-readable data interchange format that is widely used across the Internet. It uses simple key-value pairs, arrays, ordered lists, and nested objects to represent complex data structures. Its simplicity and widespread adoption make it very natural for developers to work with. Here's a simplified example of a product document in JSON. Producted P12345. Name: wireless noise-canceling headphones. Brand: Audiotech. Price: $199.99. Category: electronics, audio. Specifications: color: black. Weight grams: 250. Battery life hours: 30. Connectivity: Bluetooth 5.0, USB-C. In stock: true. Reviews: UserID U001. Rating: 5. Comment: amazing sound quality and comfort. UserID U002. Rating: 4. Comment: battery life is great but a bit pricey. Notice how a single document contains not just basic product details, but also lists like category and connectivity, nested information, specifications, and even an array of full reviews for that product. While JSON is excellent for human readability and data exchange, MongoDB actually stores its documents in a binary encoded format called BSON, binary JSON. BSON retains the JSON-like structure, but is more efficient for computers to parse and traverse. It also supports more data types than standard JSON, such as dates, 64-bit integers, and binary data, which are crucial for real-world database applications. So, you write a JSON-like document, and MongoDB handles the efficient conversion to BSON for storage. The power of BSON and JSON is that they map almost perfectly to the objects and data structures used in modern programming languages. This impedance mismatch, the difficulty of fitting object-oriented programming designs into a relational database's tabular structure, is greatly reduced, making development faster and more intuitive. 3.3 Schemaless or schema-on-read, demystifying flexibility. One of the most frequently touted features of document databases is their schema flexibility. This concept is often misunderstood as schemaless, implying a chaotic free-for-all where you can dump any data into the database without concern for its structure. This is a common misconception and a dangerous one to embrace literally. The more accurate and helpful term is schema-on-read. This means that while the database itself doesn't strictly enforce a predefined structure before data is written, unlike a relational database that requires you to declare all columns beforehand, your application implicitly defines and expects a certain structure when it reads the data. Here's how that flexibility works in practice. No upfront declaration. You don't need to create a table definition or column types before inserting your first document. You simply insert a document. Varying structures. Documents within the same collection can have different fields. For example, in a collection of user profiles, one user might have a favoritiscolor field, while another might not. A document representing a student could have fields for GPA and major, while a staff member document in the same collection might have department and hire date. Agile evolution. If your application needs to add a new piece of information, say, a loyalty tier for customers, you can simply begin adding that field to new customer documents as they are created or updated. Older documents that don't have this field yet will not cause errors. The application can be designed to gracefully handle its absence. Benefits of schema on read, rapid development. You can iterate on your application's data model quickly, without the need for time-consuming database migrations or downtime typically associated with schema changes in relational databases. Adaptability. It allows your application to evolve rapidly in response to changing business requirements, new features, or emerging data sources. Handles diverse data. Perfect for situations where data isn't perfectly uniform, like user-generated content, IoT sensor data from various devices, or evolving product specifications. Analogy, think of it like a backpack versus a precise suitcase. With a suitcase, you predefine exactly where everything goes in a rigid layout. A backpack, schema on read, allows you to throw things in, rearrange easily, and add more items, but you still need to know what you put in there to find it later, and you likely have an internal system for organization. True schemaless would be just throwing things in a pile without any thought, leading to inevitable chaos. 3.4 Navigating relationships in a document world. A common question for those new to document databases is, how do you handle relationships between data if there are no tables and joins? While document databases don't use relational joins in the same way, they absolutely handle relationships between data points, often in more application-centric and performance-optimized ways. The two primary strategies are embedding and referencing. Embedding, that contains relationship. Concept, this involves storing related data directly within the parent document. The idea is to keep data that is frequently accessed together within a single document, minimizing the number of database queries needed to retrieve a complete record. When to use. Ideal for one-to-one or one-to-few relationships, where the embedded data is primarily associated with and accessed alongside the parent document, and where the embedded data is not expected to grow indefinitely. Example. A customer document might embed their shipping address and billing address, because you almost always need to see the address when looking up a customer. Example. A blog post document could embed its author details, a tags array, and a limited number of recent comments. Benefits, single read operation. Retrieving a document also retrieves all its embedded related data, which is highly efficient. Data locality, all related data is stored together on disk, leading to faster access. Atomicity, updates to embedded fields can often occur within a single atomic write operation on the parent document, simplifying transactions. Drawbacks, document size limits. MongoDB documents have a maximum size limit, currently 16 MB, so you can't embed endlessly large amounts of data. Data duplication. If embedded data is shared, e.g., embedding the full details of a product within every order document, it can lead to data duplication and make updates to that shared data more complex. Limited querying on embedded data. While you can query on embedded fields, querying data that is deeply nested and highly duplicated across many documents efficiently can become challenging. Referencing the links to relationship. Concept. This strategy is more akin to traditional relational modeling. You store a unique identifier, like an ID, in one document that points to another document, typically in a different collection. Your application then performs separate queries to join the data by retrieving the reference document. When to use. Best for many-to-one, many-to-many relationships, or when the related data is large, is updated frequently and independently, or is shared across many different documents. Example, an order document might store an array of product IDs, but not the full product details. When viewing an order, the application would then fetch the product details for each ID from the product's collection. Example: a book document might reference an authorid, where the author's full details, bio, other books are in a separate author's collection. Benefits: reduced data duplication. Avoid storing the same large chunks of data multiple times. Independent growth. Documents can grow and be updated independently, useful if the related data changes frequently. Bypasses size limits. No single document needs to exceed the 16 MB limit due to embedded data. Drawbacks: multiple read operations. Retrieving related data requires additional queries, which can be slower than a single embedded read. Application-level joins. The joining of data is typically handled by your application code, rather than directly by the database engine in a single query, though MongoDB offers advanced aggregation features that can simulate joins. Hybrid approaches. In practice, the most effective MongoDB data models often combine both embedding and referencing. You embed small, frequently accessed, and tightly coupled relationships, while referencing larger, shared, or less frequently accessed relationships. The art of data modeling in document databases is about understanding your application's data access patterns and optimizing for read-write efficiency, not just rigid normalization rules. 3.5 A conceptual case study, building a product catalog. Let's illustrate the power of document modeling with a conceptual example, an e-commerce product catalog, the relational SQL approach. In a traditional relational database, a product might be spread across many different tables. Products table, product ID, name, price, brand. Product categories table, category ID, category name. Product category mapping table, links products to categories. Product features table, feature ID, feature name. Value, product images table, image ID, URL description. Product reviews table, review ID, product ID, user ID, rating, comment, date. To get a complete view of a product, including its features, images, and reviews, you would need to perform multiple join operations across these different tables, which can become complex and resource-intensive as the number of joins increases. The document MongoDB approach. With a document database like MongoDB, you would typically design a single, comprehensive product document that contains all the information related to that product. ID P12345, MongoDB's unique identifier for the document. Name, wireless noise-canceling headphones. Brand, Audiotech. Description, premium headphones with immersive sound and active noise cancellation. Price, $199.99. Currency, USD. Available stock, 500. Status, active. Categories, electronics, audio, headphones, array of categories. Specs, embedded subdocument for specifications. Color, black. Weight grams, 250. Battery life hours, 30. Connectivity, Bluetooth 5.0, USB-C. Driver size M, 40. Features, noise cancellation, voice assistant compatible, foldable design, array of features. Images, array of image objects. URL, images P12345 front.jpg, alt, front view of headphones. URL, images P12345 side.jpg, alt, side view showing ear cup. Reviews, array of embedded review documents, one-to-few relationship. Reviewid, R001. Userid, U001, reference to a separate user document. Username, Soundlover88. Rating, 5. Title, amazing sound quality. Comment, these headphones are incredible for travel. Date, 2023-10 to 26/10/00Z. Reviewid, R002. Userid, U002. Username, TechGeek. Rating, 4. Title, great features slightly heavy. Comment, battery life exceeds expectations, but comfort could be improved. Date, 2023-11-0, 1T1430Z. Potentially limit embedded reviews and store older ones in a separate collection. Referenced here. Relate products, P67890, P98765, array of references to other product IDs. Key advantages of the document approach here. Single query access. Fetching all the information for a product, its name, price, specifications, images, and recent reviews, often requires only a single database query to retrieve one document. This is incredibly fast and efficient. Flexible product attributes. If you need to add a new specification for a smart device, e.g., Has Voice Assistant, true, you simply add that field to the document. No schema alteration is needed across the entire database. If a t-shirt product document doesn't have battery life hours, that's perfectly fine. The field just doesn't appear in that document. Natural representation. The structure of the document naturally reflects the real-world product, making it easy for developers to understand and work with. This flexibility and the ability to retrieve rich, complete records with a single query are what make document databases, and MongoDB in particular, so powerful for modern application development. It streamlines data access and allows your data model to evolve hand-in-hand with your application's features. Chapter 4. Introducing MongoDB, your guide to the document world. 4.1. The story of MongoDB. A database for developers. MongoDB didn't emerge from an academic research lab. It was born out of a very practical need. In 2007, a software company called 10gen, later renamed MongoDB, Inc., was building a cloud service with a modern, agile approach. They quickly realized that the existing database solutions, predominantly relational, were hamstringing their development speed and making it incredibly difficult to scale for the demands of web-based applications. They found themselves constantly battling schema rigidity, complex object mapping, and the challenges of distributing data across multiple servers. So, instead of trying to fit a square peg into a round hole, they decided to build a new database from the ground up, one that would prioritize developer productivity, inherent scalability, and the flexibility needed for rapidly evolving data. Their philosophy was clear. Create a database that made developers highly productive, allowing for rapid iteration and handling of the new types of data generated by the internet. They combined the best aspects of traditional databases, such as rich querying and indexing capabilities, with the flexibility and scaling advantages of the emerging NoSQL approaches. From being a specialized alternative, MongoDB quickly grew into one of the most widely adopted NoSQL databases globally. It became a go-to choice for startups needing to scale rapidly and for enterprises looking to modernize their data infrastructure. Its user-friendly design and powerful feature set cemented its position as a leading solution for applications demanding agility, high availability, and massive scalability. 4.2 Core Concepts in MongoDB. The basics. To understand how MongoDB organizes information, let's break down its fundamental building blocks. These concepts parallel traditional database terms, but use different nomenclature to reflect MongoDB's document-oriented approach. Documents. As we discussed in Chapter 3, the document is the core unit of data in MongoDB. Each document is a self-contained, flexible, JSON-like, BSON object that represents a single record or entity. For example, a single document might describe a user, a product, an order, or a blog post. Documents are MongoDB's equivalent of a row in a relational database, but with vastly more flexibility in their internal structure. Collections. A collection in MongoDB is a group of documents. It's MongoDB's equivalent of a table in a relational database. However, unlike a table, documents within the same collection do not need to have the exact same structure. While it's common practice to group similar documents together, e.g., all user documents in a user's collection, MongoDB places no strict requirement on uniform fields. This allows for schema flexibility within a single logical grouping of data. Think of a collection as a folder filled with similar types of documents pertaining to a customer, but each customer's specific folder might have different additional papers depending on their interactions with your business. Databases. A database in MongoDB is a logical container for collections. A single MongoDB server, or a cluster of servers, can host multiple databases, each containing its own set of collections. This separation is useful for organizing different applications or environments, e.g., production of DB, development of DB. To summarize the hierarchy, you typically have a MongoDB instance, or a cluster of instances, which contains one or more databases. Each database has one or more collections, and each collection is composed of documents, which in turn contain fields, key value pairs, nested documents arrays. This clear, hierarchical structure, combined with the natural mapping of documents to objects in modern programming languages, simplifies the development process and makes it very intuitive for developers to interact with their data. 4.3 Key features that make MongoDB stand out. MongoDB's popularity stems from a suite of powerful features designed to meet the demands of modern application development. High performance by design. Leveraging RAM, MongoDB is designed to keep frequently accessed data in RAM, random access memory, whenever possible. Accessing data from memory is orders of magnitude faster than reading from disk, significantly boosting read performance. Powerful indexing. Like an excellent index at the back of a textbook, MongoDB indexes allow the database to rapidly locate specific data without scanning every single document in a collection. You can create indexes on any field, even within nested documents or arrays, greatly speeding up queries. MongoDB also supports specialized indexes for geospatial, location-based, data, and text search. Rich query language. MongoDB provides a powerful, intuitive query language that goes far beyond simple key-value lookups. You can query on any field, perform range queries, use regular expressions, and even query by specific fields within nested documents and arrays. This allows developers to express complex data retrieval needs directly to the database. Scalability and high availability, built in, this is where MongoDB truly excels for large applications. Replica sets. For high availability and data redundancy, MongoDB uses replica sets. These are groups of MongoDB servers that maintain the exact same dataset. If the primary server, where writes happen, goes down, one of the secondary servers automatically takes over, ensuring continuous operation with zero data loss within the set. This built-in failover mechanism is critical for always-on applications. Sharding. For massive horizontal scalability, handling huge data volumes and extreme traffic, MongoDB employs sharding. This process distributes large datasets across multiple independent servers or clusters, shards. Your application connects to a router that knows where all the data lives, so you don't need to manage the complexity of data distribution manually. Sharding allows MongoDB to scale almost infinitely, processing data and requests far beyond the capacity of a single server. Aggregation framework. This is a sophisticated and highly powerful feature within MongoDB for data analysis and transformation. It allows you to process data records sequentially through a series of pipeline stages, similar to an assembly line. You can filter, group, sort, reshape, and transform documents to return computed results. This enables complex analytics, report generation, and data transformations directly within the database, reducing the need to move data to external processing systems for many analytical tasks. Versatility. MongoDB's flexible schema and scalable architecture make it suitable for a wide range of applications, from agile web development to complex enterprise systems. Its design often accelerates development cycles and allows businesses to adapt quickly to changing requirements. These features collectively contribute to faster application development, greater flexibility in data modeling, and the ability to handle growth without massive re-architecture, making MongoDB a compelling choice for many modern applications. 4.4 Where MongoDB shines. Common use cases revisited. MongoDB's unique blend of flexibility and scalability makes it a natural fit for many common application types in today's data-driven world. E-commerce and product catalogs manage rapidly changing product information, new sizes, colors, features, user reviews, and dynamic pricing. The flexible document model effortlessly handles products with widely varying attributes. Content management systems, CMS, store articles, blogs, user-generated content, media files, and their associated metadata. Its schema flexibility makes it easy to support diverse content types, and rich text indexing speeds up content discovery. Mobile applications provides scalable and highly available backends for user data, push notifications, user preferences, and managing application state across millions of mobile users globally. The document model maps very closely to the object structures in mobile app code. Gaming, store player profiles, game states, real-time leaderboards, and handle massive concurrent user loads. The high write throughput and ability to flexibly store player data inventory, achievements are critical here. Personalization and user profiles easily adapt to storing new user preferences, tracking user behavior, and delivering tailored experiences and recommendations. As new data points about users become available, they can be added to user documents without requiring system-wide changes. Internet of Things, IoT, ingest and analyze enormous volumes of diverse time series data from countless devices, from smart sensors to industrial machinery. Its high write performance and flexible schema are ideal for the varied and continuous streams of IoT data. A real-world example. A mid-sized media company was struggling with a traditional database to manage their expanding library of articles, videos, and podcasts. Adding new content types or features meant cumbersome schema migrations and downtime. By migrating to MongoDB, they could roll out new content sections and features, like user comments and personalized playlists, in a fraction of the time. The flexible document model perfectly accommodated their diverse media, and MongoDB's scaling capabilities ensured their platform remained fast and available even during peak traffic events. This agility allowed them to innovate much faster and keep their audience engaged. In essence, MongoDB is designed for agility and scale. It empowers developers and businesses to build applications that are flexible enough to adapt to ever-changing requirements and robust enough to handle the immense data volumes and user traffic of the modern world. Chapter 5, Building Flexible Data Models with MongoDB. 5.1, The Art of Document Design. Thinking differently. Designing data models in a document database like MongoDB is a fundamental shift from the traditional relational mindset. In the relational world, the golden rule is normalization, breaking down data into its smallest, purest forms and distributing it across many separate tables to avoid duplication. This minimizes data redundancy and optimizes for data integrity, often assuming your primary bottleneck is disk space or updates to duplicated data. In MongoDB, the approach often leans towards denormalization, embedding related data directly within the main document. This doesn't mean forsaking good design. Rather, it means prioritizing application-level needs, especially read performance, and understanding that data access patterns are paramount. The goal is to design documents that closely mirror the data your application needs to retrieve for a single entity in a single request. It's an art more than a strict science, as there's often no single, right, way to model data. The best design for your specific document will depend on how you access your data. Will you always need a customer's address when you look up the customer? Or will you sometimes just need their name? The relationships between your data. Is it a one-to-one, one-to-many, or many-to-many relationship? The growth of your data. Will an embedded list grow indefinitely large? Does a document risk exceeding the 16 MB size limit? The frequency of updates. Is data frequently updated together or independently? This flexible approach encourages iterative design. You can start with a basic model and evolve it as your application grows and your understanding of data usage matures. 5.2, Embedding versus referencing. Deciding your relationship strategy. As discussed briefly in Chapter 3, the two primary strategies for handling relationships in MongoDB are embedding and referencing. The choice between them is crucial and impacts performance, data integrity, and flexibility. Embedding, the contains relationship. Concept, embedding means storing related data directly inside another document. This is ideal when data is inherently linked, frequently accessed together, and where the embedded data is contained within or belongs to the parent document. When to use one-to-one relationships, such as a user profile and their primary address. One-to-few relationships, where the many side is relatively small and won't grow without bound. Examples: a blog post and its few tags, a product and a small set of specifications, an order and its list of line items, if each order typically only has a few items. Data that is logically grouped, data that makes sense to retrieve as a single unit. Frequent joint reads, when you almost always need the related data when you access the parent document. Advantages: faster reads. A single query retrieves all the necessary data, minimizing trips to the database. This is a significant performance boost. Data locality: related data is stored together on disk, which can improve caching and retrieval times. Atomicity: updates to the embedded data can often be performed atomically within the context of updating the parent document, simplifying transactions for that related data. Disadvantages: document size limit. Each MongoDB document has a 16 MB size limit. Embedding excessively large or ever-growing arrays can hit this limit. Data duplication. If the embedded data needs to be shared across many parent documents, embedding it would lead to duplication. Updating that shared data would then require updating it in multiple locations. For instance, embedding a full supplier document into every product document would mean many duplicate supplier records if a supplier provides many products. Querying embedded data. While possible, querying solely on data embedded deep within an array across many documents can sometimes be less efficient than querying a top-level field in a separate collection. Referencing the links to relationship. Concept: referencing involves storing a unique identifier, typically the id field, from one document within another document. This creates a logical link, and your application then performs a separate query to follow this link and retrieve the reference document. When to use: many-to-one relationships, such as many orders referencing a single customer. Many-to-many relationships. For example, students enrolling in multiple courses and courses having many students. Large or frequently growing related data. When embedded data would push the document size limit, e.g., millions of comments on a single blog post. Shared data. When the related data, e.g., product details, category information, is shared and updated independently across many parent documents. Infrequent joint reads. When you don't always need the related data every time you retrieve the main document. Advantages: avoids duplication, reduces data redundancy, and simplifies updates to shared data, as you only need to update it in one place. Bypasses size limits, prevents documents from growing too large. Independent growth: related documents can scale and be updated independently. Disadvantages: multiple queries. Retrieving the complete related information requires at least 2 queries to the database, one for the main document, one or more for the reference documents, which can sometimes be slower than a single embedded read. Application-level joining. The application code is responsible for making the additional queries to resolve the references, effectively performing a join. Hybrid approaches. It's common and often optimal to blend both strategies. For example, a blog post might embed a few tags, one to few, frequently accessed. Embed a few recent comments, small, related, frequently accessed with the post. But use references to a separate user's collection for the author, and commenters, many posts, many comments, but user details are shared and might change independently. The decision of whether to embed or reference is one of the most critical aspects of MongoDB schema design. It fundamentally affects performance and application complexity. The key is to optimize for your most common queries and data access patterns. 5.3 Designing for performance. The role of indexes. No matter how well you structure your documents, without effective indexing, even the most elegantly designed database can grind to a halt. In MongoDB, just like in a physical library, having a good index is paramount for quick data retrieval. What is a database index? An index is a special data structure that stores a small, ordered portion of a collection's data. Its primary purpose is to enable MongoDB to quickly locate documents that match a query's criteria without having to scan every single document in the collection, a process known as a collection scan. Analogy: imagine a massive library where books are simply put on shelves in any order. If you want to find all books by Jane Austen, you'd have to walk down every aisle and read every spine. This is akin to a collection scan in a database, very slow for large collections. Now, imagine that same library with an extensive card catalog or a digital index where all books are listed alphabetically by author, title, genre, etc. To find Austen's books, you simply look up Austen in the index, find the shelf numbers, and go directly to those books. This is how an index speeds up data retrieval. How indexes work conceptually. When you create an index on a field, or multiple fields, MongoDB builds a sorted list of the values for that fields, along with pointers to the documents where those values reside. When a query comes in that uses an indexed field, MongoDB can go directly to the index, find the relevant pointers, and retrieve only the matching documents, rather than scanning the entire collection. Benefits of indexes: dramatically faster reads. Queries that use indexed fields for filtering, where, sorting order by, or finding unique values will execute significantly faster. Faster sorting. If you frequently sort your query results, an index on the sort keys can speed up the operation. Efficient unique constraints. Indexes can be used to enforce uniqueness constraints, e.g., ensuring every user has a unique email address. Types of indexes conceptually. MongoDB supports various types of indexes to suit different data types and query patterns. Single field index. On a single field, e.g., user email. Compound index. On multiple fields, e.g., user last name and user first name, useful for queries that filter or sort on multiple criteria. Multi-key index. On fields that contain arrays, allowing queries to efficiently search for elements within the array. Text index, for performing full-text search queries on string content. Geospatial index, for supporting queries on geographical coordinate data, e.g., find all restaurants within 5 miles. Trade-offs. While indexes are crucial for read performance, they come with a small overhead. Storage space. Indexes consume disk space. Write performance. Every time a document is inserted, updated, or deleted, its corresponding indexes must also be updated. This adds a slight performance cost to write operations. The key is to identify your most frequent and performance-critical queries and create indexes that support them, balancing the read benefits against the write overhead. 5.4 Real-world data modeling example. A social media profile. Let's put these concepts into practice by designing a conceptual data model for a social media user profile in MongoDB. This requires balancing ease of access, scalability, and flexibility. The user document, embedding common data. We'll start with a main user document that contains core profile details and frequently accessed, relatively small or tightly coupled information. id, user12345, MongoDB's unique identifier for this user. Username, Jane Dauphin. Email, janedoe@example.com. First name, Jane. Last name, Doe. Bio, avid reader, traveler, and amateur photographer. Profile picture. https://cdn.example.com/profiles/janedoejpg. Location, embedded subdocument. City, London. Country, UK. Coordinates, 0.1278, 51.5074, GeoJSON format for location queries. Join date, ISO date, 2021 to 3 to 15 T1000Z. Last login, ISO date, 2023 to 11 to 0 5 T1430Z. Settings, embedded subdocument for user-specific settings. Theme, dark. Notifications enabled, true. Privacy level, public. Follower count, 1289, embedded counts for quick display. Following count, 345. Post count, 76. Recent posts, embedded array for a few recent posts, 1 to few. Posted, post 789, reference to actual post document. Content summary, just landed in Kyoto, first impressions are magical. Timestamp, ISO date, 2023 to 11 to 0 4 1800Z. Posted, post 788. Content summary, new book recommendation, The Midnight Library. Timestamp, ISO date, 2023 to 11 to 0 3 T91500Z. Favorite genres, fantasy, sci-fi, travel, example of a new flexible field. Why this design? Fast profile loading. When someone views Jane's profile, almost all the immediately relevant information is in a single document, retrieved with one query. Flexible attributes. If we decide to add a favorite quotes field in the future, we just start adding it to new or updated user documents. Older documents without this field simply won't have it, and the application gracefully handles its absence. Embedded counts. Follower count, following count, post count are embedded because displaying them on a profile page is a common, quick read. These would be updated asynchronously, out of band, rather than in real time with every follow-unfollow post. Embedded recent activity. A recent posts array, limited to maybe the last 5 to 10, means we don't need a separate query for basic profile display. Handling larger or frequently changing related data, referencing. For data that is very large, grows frequently, or is shared across many users, we would use referencing. Posts collection. A separate collection to store the full details of every post. The user document only embeds a summary or reference to recent posts. All of Jane's 76 posts and their associated comments, likes, high-res images would reside here. Followers and following collections, or a single relationships collection. Storing millions of follower-following relationships within a user's document would lead to massive, unwieldy documents. Instead, these would be in separate collections linking user IDs. For example, a relationships collection document might look like followerid, user 54321, followingid, user 12345. Messages collection. Direct messages, being numerous and dynamic, would reside in their own collection, referencing the sender and recipient user IDs. Conceptual process. When Jane's profile page loads, the application retrieves her user 12345 document. Basic info, recent post summary, and counts are displayed instantly. If a user clicks View All Posts or See All Followers, the application then makes additional, targeted queries to the posts or relationships collections using Jane's ID schema evolution in action. A growing social app initially only tracked username and email. As it gained users, it needed to add profile picture, bio, and location. In a relational database, this would involve altering tables. In MongoDB, they simply started creating new user documents or updating existing ones with these new fields. The location field could start as a simple string, then later evolve into a nested object with city, country, and geospatial coordinates when location-based features were introduced. This agile data evolution allowed them to quickly ship new features without significant database overhead. By thoughtfully combining embedding and referencing, and by strategically applying indexes, developers can build highly performant, flexible, and scalable social media applications on MongoDB, showcasing its power in handling complex, evolving data. Chapter 6, Scaling Up and Out, MongoDB's Distributed Architecture. 6.1, The Challenge of Scale, Why One Server Isn't Enough. In the early days of computing, and for many smaller applications today, a single computer server is perfectly adequate to host an application and its database. This approach, known as vertical scaling, or scaling up, involves making that single server more powerful by adding more CPUs, more RAM, and faster storage. It's like buying a bigger, faster oven for an increasingly popular bakery. While effective up to a point, vertical scaling eventually hits fundamental limitations, physical limits. There's only so much memory or processing power you can cram into a single machine. Cost. High-end, multi-processor servers become exponentially more expensive as you try to squeeze out the last bits of performance. Single point of failure. If that one powerful server goes down due to hardware failure, power outage, or any other issue, your entire application is offline. Modern businesses simply cannot afford this downtime. The internet boom, with its millions or billions of concurrent users and petabytes of data, quickly demonstrated that scaling up was not a sustainable long-term strategy for truly massive applications. A new paradigm was needed: horizontal scaling, or scaling out. This involves distributing data and processing across a multitude of smaller, often cheaper, servers. It's like opening multiple smaller bakeries across the city, each with its own oven, to serve more customers and ensure that if one oven breaks, others are still baking. MongoDB was designed from the ground up with horizontal scalability and high availability as core tenets. It provides built-in features that simplify the deployment and management of distributed database systems, enabling applications to handle immense data volumes and user traffic with continuous uptime. 6.2 High availability with replica sets, the power of copies. When your application cannot afford to go offline, you need high availability. MongoDB achieves this through replica sets. A replica set is a group of MongoDB processes, servers or nodes, that maintain the exact same dataset, providing redundancy and ensuring continuous operation in case of failures. Here's how a replica set works conceptually. Primary, master node. Within a replica set, one node is designated as the primary. This is the node that receives all write operations, inserting, updating, deleting data from your application. It acts as the main point of contact for changes to your data. Secondary, slave nodes. The other nodes in the replica set are secondaries. They continuously replicate data from the primary. This means they apply all the changes made on the primary to their own data copies, keeping them up to date. Secondaries can also serve read operations, distributing the read load and improving overall performance, especially for read-heavy applications. Automatic failover. The most compelling feature of replica sets is their ability to handle failures automatically. If the primary node ever becomes unavailable due to a network outage, hardware failure, or planned maintenance, the secondary nodes automatically hold an election. Through this election process, one of the secondaries is rapidly promoted to become the new primary. This transition happens seamlessly, often without your application even noticing a disruption. Data redundancy. By maintaining multiple copies of your data across different servers, replica sets protect against data loss. Even if one server fails completely, your data is safe on the other secondaries. Distributed geographically. For enhanced disaster recovery, you can even place replica set members in different data centers or cloud regions, ensuring your application remains online even if an entire data center goes down. Think of a priceless historical document. You wouldn't just have one copy. You'd have the original, the primary, and several exact duplicates, secondaries, stored in different, secure archives. If the original copy is ever compromised or destroyed, another duplicate is immediately declared the new official version, ensuring the information is never lost and work can continue without interruption. This is the essence of a MongoDB replica set. 6.3 Horizontal scalability with sharding, dividing and conquering. While replica sets provide high availability and data redundancy for a single dataset, when your data grows to terabytes or petabytes, or your application needs to handle millions of operations per second, a single replica set will eventually reach its limits. This is where sharding comes in. Sharding is MongoDB's method for distributing a large dataset and its accompanying workload across multiple independent database servers, or replica sets. It allows MongoDB to overcome the limitations of a single machine and scale horizontally to handle truly massive datasets and extremely high throughput. Here's a conceptual breakdown of sharding. Shards. A shard is an independent MongoDB instance, or, more commonly and for reliability, a replica set that holds a portion of the overall data. Imagine a massive library where instead of all books being in one building, they are divided into multiple smaller buildings, each specializing in a certain range of authors or genres. Query routers, Mongos. Your application doesn't connect directly to an individual shard. Instead, it connects to a query router, known as Mongos. This intelligent router knows exactly how the data is distributed across all the shards. When your application sends a query, the query router directs it to the correct shards that hold the relevant data, making the sharded cluster appear as a single, large database to your application. Config servers. These store metadata about the sharded cluster. This includes information about the ranges of data each shard is responsible for, allowing the query routers to efficiently route requests. The shard key. This is the most crucial concept in sharding. A shard key is one or more fields within your documents that MongoDB uses to determine how to distribute data across the shards. Choosing an effective shard key is vital for efficient data distribution and query performance. For example, in a social media application, you might shard user data based on their user ID or geographic location. This ensures that all data for a specific user resides on a single shard, or at least a limited number of shards, and that queries related to that user can be efficiently routed. Benefits of sharding: massive data capacity. Sharding allows you to store datasets that are far too large to fit on a single server. As your data grows, you simply add more shards. High throughput. By distributing read and write operations across many servers, a sharded cluster can handle a much higher volume of concurrent operations than a single server. Scalability for growth. As your application's data or user base expands, you can dynamically add new shards to increase capacity and speed without significant downtime. Geographic distribution. You can place shards in different physical locations, data centers or cloud regions, to bring data closer to users, reducing latency, and provide a greater degree of disaster recovery. Consider a global messaging platform. It might shard user data by geographic region, e.g., North American users on one shard, European users on another, or by a range of user IDs. This ensures that a single user's data is on one shard, but the millions of users and their billions of messages are distributed efficiently across hundreds of servers. A new message from a user in New York would be routed to the North American shard, while a message from Tokyo would go to an Asian shard. 6.4. The distributed advantage. More resilient, more powerful. When replica sets and sharding are combined, they create an incredibly robust, resilient, and highly performant distributed database architecture. Each shard in a sharded cluster is typically its own replica set, meaning that even a single shard benefits from the high availability and data redundancy of replication. Your data is not only spread across multiple machines, eliminating the single point of failure and bottleneck of one server, but each piece of that data is also redundantly copied. This architecture enables MongoDB to support some of the strongest applications in the world, handling massive data intake, providing real-time data access for millions of users, and ensuring continuous operation. Critically, these capabilities are built-in features of MongoDB, significantly simplifying the complexities of distributed systems for developers and operations teams compared to older, manual approaches. This is a testament to MongoDB's commitment to enabling applications to scale dynamically with business growth and meet the demanding requirements of the connected world. Chapter 7. Querying and analyzing your documents. 7.1. Finding your data. Basic queries in MongoDB. Once you've structured your data elegantly into documents and collections, the next crucial step is being able to retrieve, manipulate, and analyze that data. Interacting with data in MongoDB is designed to be intuitive, resembling how you might naturally describe what you're looking for, rather than requiring complex, rigid database-specific code. MongoDB's query language, which is JSON-based, allows for expressing powerful queries in a way that feels natural to modern application developers. Let's explore the fundamental operations for interacting with your data. Inserting documents. Adding new data to a MongoDB collection is straightforward. You simply provide a complete JSON-like object, a document representing the new record, and MongoDB places it into the specified collection. Conceptually, you're telling the database, here's a new product document with its name, price, and description. Please put it into the products collection. Finding documents. Retrieving data from a collection is done using a find operation. The power comes from specifying criteria within a JSON-like object that tells MongoDB which documents you want. Finding all documents. If you provide an empty query object, e.g., MongoDB will return all documents in a collection. Finding by a single field. You can search for documents where a specific field has a certain value. Conceptually, show me all the documents in the customer's collection where the city field is New York. Finding by multiple fields. You can combine conditions to narrow down your search. Conceptually, show me all product documents where the category is electronics and the brand is audio tech. Finding within nested fields. MongoDB allows you to query fields that are nested within subdocuments using dot notation. Conceptually, find all user documents where the address zip code field is 10,001. Updating documents. Modifying existing documents is also flexible. You can update specific fields within a document or even replace an entire document. Conceptually, for the user document with the ID, user12345, please set their email field to new@example.com. You can also increment numerical values, increase the product's view count by 1, remove fields, or add new ones. Deleting documents. Removing documents from a collection is similarly direct. You specify the criteria for the documents you wish to remove. Conceptually, delete all order documents that are marked as status, canceled, and are older than a certain date. The strength of MongoDB's basic query language lies in its expressiveness and its direct mapping to the document structure. It feels less like writing database code and more like describing the data you want to retrieve or modify. 7.2 Filtering and sorting. Precision data retrieval. MongoDB's query language goes beyond simple exact matches, providing powerful operators to filter, compare, and arrange your data with precision. Applying criteria with operators. To perform more complex filtering, MongoDB uses special query operators, which typically begin with a $sign. These allow you to specify conditions like greater than, less than in a list, and so on. Comparison operators. GT greater than, LT less than, GTE greater than or equal to, LTE less than or equal to. Find all product documents where the price is GT 50.00, NI not equal to. Find all user documents where the status is NI inactive. In value is in an array of possibilities. Find order documents where the status is in pending, processing, logical operators, and, or not. Combine multiple conditions. Find product documents where the category is electronics and the price is LT 100.00. This enables very specific data targeting. Element operators. Check for the existence or type of fields. Exists. Find all user documents that have a phone number field. Sorting results. Once you've retrieved your documents, you often need them presented in a specific order. MongoDB allows you to sort results based on one or more fields in either ascending or descending order. Conceptually, show me all user documents, sorted first by their last name in ascending order, and then by their first name in ascending order for users with the same last name. Limiting and skipping results, pagination. For applications dealing with large datasets, it's common to retrieve only a subset of documents or to implement pagination for displaying results across multiple pages. Limiting, retrieve only a specific number of matching documents. Conceptually, give me the top 10 best-selling product documents. Skipping, skip a certain number of documents before returning the results. Used in conjunction with limit for pagination. Conceptually, show me the next 10 blog post documents after the first 20. This would be skip 20, limit 10. Projecting fields, shaping output. Often, you don't need every field from a document. MongoDB allows you to specify exactly which fields you want to include or exclude from the query results. This reduces the amount of data transferred and processed, improving performance. Conceptually, for all user documents, just show me their username, email, and profile picture, but not their entire profile details or settings. These filtering, sorting, limiting, and projection capabilities provide powerful tools for precisely retrieving and shaping the data you need from your MongoDB collections. 7.3 The Aggregation Framework. Transforming and summarizing data. While find queries are excellent for retrieving individual documents or subsets, the aggregation framework is MongoDB's powerful tool for processing data records and returning computed, transformed, or summarized results. Think of it as a sophisticated data processing assembly line or a multi-stage funnel. Raw documents go in at one end, pass through various processing stages, and come out as transformed, summarized, or enriched results at the other end. Each stage performs a specific operation on the documents as they flow through. The aggregation framework is extremely versatile and can be used for data transformation, reshaping documents, creating new fields, or combining existing ones. Filtering and grouping, performing advanced filtering and then grouping documents to calculate aggregate values, like sums, averages, counts, minimums, maximums. Data analysis, generating reports, building dashboards, and extracting insights from your data directly within the database. Simulating joins. While not traditional joins, the aggregation framework's lookup stage allows you to perform left-outer joins to combine documents from other collections. Key aggregation stages, conceptually. Match. This is usually the first stage in an aggregation pipeline. It filters documents to include only those that match specified conditions, similar to a find query or a SQL where clause. Project reshapes documents. You can select, rename, add, or remove fields to achieve the desired output structure. Group groups documents by a specified fields and performs aggregate calculations on the grouped data. This is where you calculate sums, averages, counts, etc. Example: group all order documents by custom RID and then calculate the total amount spent by each customer. Sort sorts the documents in the aggregation pipeline. Limit restricts the number of documents passed to the next stage. Unwind used to deconstruct an array field from the input documents to output a document for each element. This is useful for processing array elements individually. Conceptual example: let's say you want to answer the question, calculate the total revenue generated by each product category last quarter. Match. You'd first filter, match, all order documents from the last quarter. Unwind. Then, if your order documents have an array of items within them, you might unwind that array so each item within an order becomes a separate document for processing. Lookup. You might then perform a lookup to bring in product details, including their category, from a separate products collection based on producted. Group. Next, you'd group these items by their product.category. Sum. Within each group, you would calculate the sum of the item price or item price asterisk item quantity to get the total revenue for that category. Sort. Finally, you might sort the results to see the top-performing categories first. The aggregation framework allows for incredibly powerful and flexible data manipulation directly within MongoDB, reducing the need to extract data to external reporting tools for many common analytical tasks. 7.4 Beyond Basic Queries. Advanced Capabilities, Conceptual. MongoDB extends its querying capabilities with specialized features designed for specific data types and complex scenarios. Text search. MongoDB provides powerful full-text search capabilities, similar to how a search engine works. You can index textual content within your documents, e.g., article bodies, product descriptions, user comments, and then perform natural language queries to find relevant documents. This is invaluable for building search functionalities within your applications. Geospatial queries. For location-aware applications, MongoDB offers robust geospatial indexing and querying. You can store geographical data, points, lines, polygons, and perform queries like: find all coffee shops within 5 miles of my current location. Identify all delivery drivers currently located within this specific neighborhood polygon. Calculate the nearest landmark to a given point. Transactions, multi-document. Historically, a perceived limitation of some NoSQL databases was their lack of multi-document ACID transactions. While MongoDB has always provided ACID guarantees at the document level, meaning an update to a single document is atomic, modern MongoDB versions now support multi-document ACID transactions across replica sets and even sharded clusters. This means you can perform complex operations that involve modifying multiple documents, ensuring that all changes are either successfully committed or entirely rolled back, providing enterprise-grade data consistency guarantees when needed. These advanced capabilities demonstrate MongoDB's commitment to being a versatile, comprehensive database solution that meets the intricate demands of modern application development, enabling developers to build sophisticated features directly into their applications with confidence. Chapter 8, MongoDB in Action, Real-World Applications. 8.1, The Versatile Database, MongoDB Across Industries. By now, you should have a solid understanding of MongoDB's core strengths. Its flexible document model, powerful query language, and built-in capabilities for high availability and massive horizontal scalability. But how do these technical features translate into real-world value? The answer lies in MongoDB's remarkable versatility enabling it to power a vast array of applications across diverse industries. MongoDB is not a niche database. It's a general-purpose NoSQL database that excels in scenarios where agility, scalability, and handling diverse data types are critical. It acts as a foundational component for digital transformation initiatives, allowing organizations to innovate faster, deliver richer user experiences, and effectively manage the ever-increasing floods of data. In this chapter, we'll explore several conceptual case studies, showcasing how MongoDB's features help solve challenging business problems and unlock new possibilities in various domains. Each example will highlight a common industry challenge and how MongoDB provides a compelling solution. 8.2 Case Study 1: E-commerce and retail. The challenge: online retail businesses are in a constant state of flux. They deal with rapidly changing product inventories, seasonal promotions, dynamic pricing, user reviews, personalized recommendations, and massive traffic spikes during sales events. Traditional relational databases often struggle with schema evolution. Every new product line or feature, e.g., smart home devices needing connectivity protocols, clothing needing fabric material, requires schema changes that can be cumbersome and time-consuming. Scalability for peak loads. The Black Friday effect means databases must handle sudden, enormous surges in user traffic and transactions, which can overwhelm vertically scaled systems. Rich product data. Storing varied product specifications, multimedia content, and nested review data in a rigid tabular structure often leads to complex designs and slow queries. The MongoDB solution. MongoDB's features are ideally suited for the demands of e-commerce. Flexible product catalog. The document model allows each product to have unique attributes. A shirt can have size and color arrays, while a laptop can have processor type and RAMGB. New attributes can be added instantly without altering the entire database schema, accelerating the launch of new products or variants. User reviews and ratings can be embedded within product documents or referenced, making it fast to fetch a product and its feedback together. Shopping carts and order history. Flexible documents can store dynamic shopping cart contents, temporary states, and comprehensive order details, including all line items and customer information, simplifying order processing and analysis. Scalability for traffic spikes. Replica sets provide continuous availability so the site never goes down during peak shopping seasons. Sharding distributes product and order data across multiple servers, ensuring the system can handle millions of concurrent users and transactions without performance degradation. Personalization. User profiles in MongoDB can store browsing history, preferences, and past purchases, enabling real-time personalized product recommendations and targeted promotions. Benefit: faster time to market for new products and features, improved website performance even under heavy loads, and a richer, more personalized shopping experience for customers. 8.3 Case Study 2: Internet of Things, IoT, and Sensor Data. The challenge: the Internet of Things generates an unprecedented volume of data from countless connected devices, ranging from smart home sensors to industrial machinery. This data comes in wildly varying formats: temperature, pressure, GPS coordinates, humidity, machine status, and needs to be ingested, stored, and analyzed in real time. Key challenges include massive ingestion rates, handling millions of continuous data points per second from distributed devices. Schema variability. Different devices and sensor types produce different sets of data, making a fixed schema impractical. Real-time analytics. The need to process incoming data rapidly to detect anomalies, trigger alerts, or provide immediate operational insights. The MongoDB solution. MongoDB's design principles perfectly align with IoT requirements. High write throughput. MongoDB is engineered for high-volume writes, enabling it to efficiently ingest continuous streams of data from countless devices. Flexible schema for sensor data. A single collection can store documents from various sensor types. A temperature sensor document might have temperature and humidity fields, while a GPS sensor document might have latitude, longitude, and altitude. New sensor types can be integrated without requiring database downtime or schema migration. Specialized features like time series collections further optimize this. Real-time processing and analytics. The aggregation framework can process incoming sensor data to detect anomalies, e.g., sudden temperature spikes indicating a potential malfunction, calculate averages over time, identify trends, or summarize data for dashboards, providing immediate insights and enabling automated responses. Scalability and geographic distribution. Sharding allows distributing data from millions of devices across global clusters, ensuring local data processing and low latency, while handling the immense data volume. This supports use cases like smart cities, connected cars, and predictive maintenance. Benefit: efficient collection and analysis of vast datasets from the edge, enabling capabilities like predictive maintenance, environmental monitoring, smart infrastructure, and optimizing supply chains. 8.4 Case Study 3. Content Management and Digital Media. The challenge: publishers, streaming services, and social media platforms manage an ever-growing library of diverse content. Articles, videos, images, audio, user-generated comments, and metadata. Content needs to be easily searchable, updated frequently, and delivered rapidly across various devices and platforms. Challenges include diverse content types. An article has a body text, an author, and a publication date. A video has a duration, resolution, and language tracks. Supporting all these in a uniform schema is difficult. Rich search experiences. Users expect powerful search capabilities, including full-text search and filtering by various attributes. Scalability for peak audience. Delivering content to millions of concurrent viewers or readers requires a highly performant and scalable backend. The MongoDB solution. MongoDB's flexibility shines in content management. Flexible content model. A single document can represent an article, a video, a podcast episode, or a user comment, each with its unique set of attributes. This allows for unified content management while accommodating the specific needs of different media types. Rich text search. MongoDB's built-in text search capabilities allow users to find relevant content quickly based on keywords, phrases, or categories, similar to a powerful search engine. User-generated content, UGC. Managing comments, ratings, forum posts, likes, and shares is straightforward with the flexible document model, which can easily store varying data points for each interaction. Personalization and recommendations. User profiles storing viewing history, reading habits, and preferences enable tailored content recommendations, improving user engagement. Performance and scalability. Replica sets ensure content availability, and sharding supports delivering content to massive global audiences. Benefit: agile content creation and delivery, dynamic websites and apps, improved content discovery, and personalized user experiences that keep audiences engaged. 8.5 Case Study 4. Gaming and Entertainment. The challenge: online games, virtual worlds, and streaming services face extreme demands. Millions of concurrent players, real-time updates to game states and player profiles, complex player inventories, leaderboards, and the absolute requirement for zero downtime. Data consistency, low latency, and high throughput are paramount. The MongoDB solution. MongoDB is a popular choice for gaming backends due to its high write performance, rapidly saving player actions, game state changes, inventory updates, and in-game economy transactions. Flexible player profiles. A single document can comprehensively store all of a player's dynamic attributes, inventory items, achievements, cosmetics, and statistics, which often change rapidly and can be quite complex. Real-time leaderboards. The aggregation framework enables real-time calculation and display of global or regional player rankings, keeping players engaged. Global scalability and low latency. Sharding allows distributing player data across the globe, bringing data closer to players to minimize latency. This supports massive multiplayer online, MMO games, and ensures smooth gameplay for millions. Replica sets provide continuous play by offering high availability and rapid failover. Benefit: seamless, responsive gameplay, robust backend infrastructure for massive multiplayer games, and the flexibility to rapidly introduce new game features or items without disrupting service. 8.6 Broader applications: healthcare, financial services, logistics. MongoDB's versatility extends far beyond these examples, permeating many other industries undergoing digital transformation. Healthcare: managing flexible patient records that can adapt to new medical findings, diagnoses, or treatments. Storing and analyzing medical device data or clinical trial results. Its ability to accommodate unstructured notes alongside structured data is highly valuable. Financial services: storing credit card transaction data, fraud detection logs, diverse market data with unique attributes, and compliance data. The need for real-time analytics and high transaction volumes makes MongoDB attractive, especially with its support for multi-document ACID transactions. Logistics and supply chain: tracking packages with varying attributes, managing warehouse inventories, optimizing delivery routes using geospatial data, and handling rapidly changing shipping manifests. Building digital twins of physical assets. In each of these diverse scenarios, MongoDB provides an adaptable, performant, and scalable solution, proving itself as a foundational technology for building the next generation of data-driven applications that demand agility and innovation. Chapter 9: Administering MongoDB, Keeping Your Data Safe and Sound. 9.1 The Importance of Database Administration. Conceptual: building and deploying a powerful MongoDB application is only half the battle. Once in production, your database becomes a critical asset, holding the lifeline of your business's data. Ensuring that this data is safe, consistently available, and performing optimally requires a dedicated focus on database administration, often abbreviated as DBA. While MongoDB's design aims to simplify many operational aspects, especially with its built-in replication and sharding capabilities, it is not a set-it-and-forget-it system unless you're leveraging a fully managed service, which we'll discuss shortly. Just like owning a high-performance sports car, having MongoDB gives you incredible power and speed, but it still needs regular oil changes, tire rotations, and protective measures to keep it running smoothly and safely. The role of database administration, whether handled by a dedicated professional, a DevOps team, or automated tools, is to proactively manage the database throughout its lifecycle. This involves ensuring data integrity, protecting against corruption and loss, maximizing performance, tuning the database so applications run fast and remain responsive, guaranteeing availability, minimizing downtime, and ensuring the database is always accessible, implementing security, protecting sensitive information from unauthorized access, planning for growth, ensuring the database can scale to meet future demands. Neglecting these aspects can lead to performance bottlenecks, downtime, data loss, or security vulnerabilities, all of which can severely impact your business and customer trust. Proactive administration is about preventing problems before they become crises. 9.2 Securing your MongoDB deployment. Security is paramount for any database, especially when dealing with sensitive information. MongoDB provides a comprehensive set of features to help you protect your data from unauthorized access. A robust security strategy involves multiple layers. Authentication: this is the process of verifying a user's identity. Are you who you say you are? MongoDB supports various authentication mechanisms, including username and password, the most common form where users provide credentials. MongoDB encrypts passwords and offers robust hashing algorithms. SCRAM, Salted Challenge Response Authentication Mechanism, a secure method that prevents passwords from being sent over the network in plain text. X.50 9 Certificate Authentication, a more advanced method using digital certificates for enhanced security, often used in production environments. LDAP/Kerberos integration, for integrating with existing enterprise directory services, simplifying user management. Authorization: once a user is authenticated, authorization determines what they are allowed to do. What can you access or modify? MongoDB implements role-based access control, RBAC. You define roles that encapsulate sets of permissions, e.g., read-only access to a specific collection read-write access to a database, or administrative privileges. You then assign these roles to users. This ensures that users only have the minimum necessary access to perform their tasks, following the principle of least privilege. For instance, a common user might only have permission to read from the product's collection, while a product manager might have read and write access to it. Encryption, protecting data from being read by unauthorized parties. Encryption in transit, TLS/SSL. This secures data as it travels over the network, for example, between your application and the MongoDB server. Just like secure websites use HTTPS, MongoDB connections can be encrypted using TLS/SSL to prevent eavesdropping. Encryption at rest. This secures data stored on disk. If a hard drive is stolen, the data on it remains unreadable. This can be achieved through file system encryption, operating system-level encryption of the entire disk. Volume encryption, encrypting specific storage volumes. MongoDB's Wired Tiger storage engine encryption, enterprise-grade encryption that can encrypt individual database files. Network security, controlling who can even connect to your database. This involves firewalls, configuring network firewalls to restrict database access only to trusted IP addresses or networks, e.g., only your application servers. Private networks VPNs, deploying databases within private virtual networks or requiring VPN connections to access them, isolating them from the public internet. Security is not a one-time setup. It's a continuous process that requires vigilance, regular audits, and staying informed about best practices and potential vulnerabilities. 9.3 Backups and recovery. Your data safety net. No matter how robust your database infrastructure, hardware can fail, software can have bugs, and human error can occur. A well-defined and regularly tested backup and recovery strategy is your ultimate safeguard against data loss. Without solid backups, a critical failure could lead to catastrophic business consequences. Why backups are essential: hardware failure, disk crashes, power supply failures, or entire server outages. Human error, accidental deletion of data, incorrect updates, or misconfigurations. Software bugs, application bugs that corrupt data. Malicious attacks, ransomware or data destruction by attackers. Conceptual backup strategies. MongoDB offers several approaches for backups. File system snapshots. For databases deployed on virtual machines or cloud volumes, you can often take a complete snapshot of the database's data files. This creates a point-in-time copy that can be restored. MongoDB's MongoDump utility. This command line tool connects to a running MongoDB instance and exports the database's data to BSON files. These files can then be compressed and stored. The corresponding MongoStore tool imports the data back. This is simple for smaller databases. Replica set rollback/oplog replay. For more advanced point-in-time recovery to very granular moments, you can leverage MongoDB's replication log, oplog. The oplog records all write operations, allowing you to replay changes up to a specific timestamp, effectively restoring your data to nearly any moment in time. Cloud provider managed backups. If you use cloud-hosted MongoDB, like MongoDB Atlas, the cloud provider typically offers automated, scheduled, and highly reliable backup solutions built into their service. The importance of testing recovery. A backup is only as good as its ability to be restored successfully. It is absolutely critical to regularly test restores. Periodically perform a full restore of your backups to a non-production environment. This verifies that your backup files are intact, your procedures are correct, and you can actually recover your data when truly needed. Automate where possible. Automate your backup processes to ensure consistency and reduce the chance of manual error. Think of it like this: you wouldn't just buy a fire extinguisher, you'd also learn how to use it and occasionally check if it's still charged. The same goes for your data's safety net. 9.4 Monitoring and performance tuning, high level. Even the most well-designed database can suffer from performance issues if not properly monitored and tuned. Constant vigilance helps maintain optimal performance and prevents small issues from escalating into major problems. What to monitor: server resources, CPU usage, Is the CPU consistently maxed out, indicating a bottleneck? Memory usage. Is the database using all available RAM, leading to disk thrashing? Disk I/O. Are read-write operations on the disk becoming a bottleneck? Network throughput. Is the network saturated? Database-specific metrics. Connections. Are too many connections overwhelming the database? Query performance. Which queries are slow? Are indexes being used effectively? Write operations. Is the write load manageable? Replication lag. Are secondaries falling behind the primary in a replica set? Page faults. Is the database constantly loading data from slow disk into faster memory? Tools for monitoring. MongoDB provides built-in commands and utilities, MongoStat, MongoTop, for basic, real-time monitoring. For comprehensive, historical monitoring and alerts, more sophisticated solutions are used. MongoDB Atlas provides detailed, intuitive dashboards for monitoring every aspect of your cluster. Third-party monitoring tools. Many external solutions offer deep insights and integration with alerting systems. Performance tuning concepts. Index optimization, the most common and impactful performance tuning technique. Analyzing slow queries, often identified through monitoring, and creating appropriate indexes can dramatically improve read performance. It's like adding more specific routes to your library's index so people can find books even faster. Query optimization. Rewriting inefficient queries or adjusting the way your application accesses data can yield significant gains. Data model review. Periodically revisiting your data model to ensure it still aligns with your application's access patterns and to adjust embedding referencing strategies. Hardware sizing. Ensuring your servers have adequate CPU, RAM, and fast storage for your workload. Configuration tuning. Adjusting MongoDB's configuration parameters based on your specific workload and environment. Proactive monitoring and thoughtful performance tuning are essential to ensure your MongoDB deployment remains fast, reliable, and responsive as your application and data grow. 9.5. The rise of managed cloud services. MongoDB Atlas. Managing database infrastructure can be complex, time-consuming, and requires specialized expertise. For many organizations, especially those focused on rapid application development, the overhead of self-managing a database can be a significant burden. This is where MongoDB Atlas comes in. MongoDB Atlas is MongoDB Inc.'s official, fully managed global cloud database service. It runs on the leading public cloud providers, Amazon Web Services, Google Cloud Platform, and Microsoft Azure. What MongoDB Atlas does for you. Instead of you setting up and maintaining servers, Atlas handles all the operational aspects of running MongoDB clusters. Automated provisioning and deployment. Spin up a new cluster in minutes across any region or cloud provider. Automated operating system and database patches upgrades. Atlas ensures your database is always running on the latest secure and stable versions. Automated backups and point-in-time recovery. Comprehensive backup strategies are managed for you with flexible restoration options. Built-in monitoring and alerting. Detailed performance metrics and customizable alerts are provided out of the box. Auto-scaling and auto-healing. Automatically adjusts resources as your needs change and recovers from failures without manual intervention. Advanced security features. Includes network isolation, encryption, IP whitelisting, and robust access controls. Global clusters. Easily distribute your data across multiple regions and clouds for low-latency access worldwide and enhanced disaster recovery. Benefits of using MongoDB Atlas. Simplified operations. Drastically reduces the operational burden on your team, allowing developers to focus on building features rather than managing infrastructure. Faster time to market. Spend less time on setup and maintenance, more time on innovation. Cost effectiveness. Often more economical than hiring dedicated DBAs and managing complex infrastructure, especially considering the total cost of ownership. Guaranteed performance and uptime. Backed by SLAs, service-level agreements from MongoDB Inc., ensuring high reliability. Global reach. Deploy your data close to your users anywhere in the world. Using MongoDB Atlas is like simply calling a ride-sharing service when you need to travel. You just tell it where you want to go, and they handle all the cars, maintenance, and drivers for you. For many modern applications, Atlas is the preferred choice for its ease of use, reduced operational overhead, and enterprise-grade reliability, allowing your team to focus on what they do best: building amazing software. Chapter 10, The Future of Data, MongoDB's Role in a Connected World. 10.1 Recap, MongoDB's Enduring Strengths. We've journeyed through the landscape of modern data management, from the limitations of traditional databases to the rise of NoSQL, and finally, to the robust capabilities of MongoDB. It's clear that MongoDB didn't just emerge as a fleeting trend. It established itself because it fundamentally addresses the inherent challenges of the modern digital era. Let's quickly recap the enduring strengths that solidify MongoDB's position as a leading database solution. Unparalleled flexibility. The document model, coupled with a schema-on-read approach, offers agility that traditional databases cannot match. It allows applications to adapt and evolve rapidly, a critical advantage in today's fast-paced, iterative development environments. Built-in scalability. Designed for horizontal scaling from day one, MongoDB effortlessly handles massive data volumes and user traffic. Its native support for replica sets ensures high availability and data redundancy, while sharding provides a powerful mechanism to distribute data across vast clusters, enabling near-limitless growth. Exceptional performance. Through smart indexing, efficient storage, and an optimized query engine, MongoDB delivers high-speed data access, meeting the demands of applications that require real-time responsiveness. Developer productivity. With its intuitive, JSON-like query language, natural mapping to modern programming language objects, and a rich ecosystem of tools and drivers, MongoDB significantly streamlines the development process, allowing teams to build features faster and more efficiently. Versatility in application. As demonstrated by its widespread adoption across e-commerce, IoT, gaming, content management, and finance, MongoDB proves its utility in an incredibly broad range of use cases, adapting seamlessly to diverse data types and business needs. The core message remains clear. MongoDB empowers agile application development by providing a flexible, scalable, and intuitive NoSQL database solution built for the dynamic, data-rich demands of the 21st century. 10.2 MongoDB and Emerging Technologies. The pace of technological change continues to accelerate, and data remains at the epicenter. What makes MongoDB particularly compelling for the future is its continuous evolution and strategic alignment with emerging technological trends. Artificial intelligence, AI, and machine learning, ML. AI and ML models thrive on large, diverse datasets. MongoDB serves as an excellent data store for both the unstructured and semi-structured data needed for training these models, as well as for storing the outputs and features derived from them. Its ability to handle varied data types and scale for massive volumes makes it an ideal backend for AI, ML-driven applications. Serverless computing. The rise of serverless architectures like AWS Lambda, Azure Functions, Google Cloud Functions, demands databases that are highly scalable, performant, and cost-effective on demand. MongoDB's managed services, particularly MongoDB Atlas, integrate seamlessly with serverless functions, allowing developers to build highly scalable, event-driven applications without managing any underlying infrastructure. Edge computing. As more data is processed closer to its source, at the edge of the network, on devices themselves or local gateways, databases that can operate efficiently in constrained environments and synchronize data back to the cloud become crucial. MongoDB's smaller footprint deployments and synchronization capabilities are well suited for these emerging edge computing scenarios. Multi-cloud and hybrid cloud strategies. Organizations are increasingly adopting multi-cloud strategies or hybrid models, combining on-premises and cloud infrastructure. MongoDB, especially through Atlas, offers unparalleled flexibility to deploy and manage data across different cloud providers and even link to on-premises deployments, preventing vendor lock-in and leveraging the best of each environment. Real-time analytics and data lakes. MongoDB can serve as a powerful operational data store that feeds into larger data lake architectures for deeper, historical analysis. Tools within MongoDB, like the aggregation framework and specialized connectors, facilitate real-time data movement and analysis, enabling businesses to derive immediate insights from their data. MongoDB is not a static technology. It continuously adapts and innovates to meet the demands of tomorrow's applications, solidifying its relevance in an ever more connected and intelligent world. 10.3 The Evolving Data Landscape. NoSQL's continued relevance. The trends that initially fueled the NoSQL movement, the explosion of big data, the need for agile application development, and the demand for always-on, globally accessible services are only accelerating. Data never stops growing. The proliferation of IoT devices, global digital economies, and hyperconnected user bases means data volumes will continue to skyrocket. Agility is paramount. Businesses must be able to adapt quickly to market changes, new customer demands, and competitive pressures. The ability to rapidly iterate on features, often involving schema changes, is a competitive advantage. Experience is king. Users expect instantaneous responses and highly personalized experiences from their applications, demanding low-latency data access at scale. In this dynamic environment, the ability to choose the right tool for the right job becomes increasingly critical. Relational databases will continue to thrive in scenarios requiring strict transactional integrity and complex reporting on highly structured data. But NoSQL databases, with MongoDB as a powerful frontrunner, will remain indispensable for building the agile, scalable, and resilient applications that define the modern digital experience. They represent the backbone of the connected world, enabling innovation and speed where traditional approaches might falter. 10.4 Final thoughts. Embracing the future of data. We stand at an exciting juncture in the history of data. Databases are no longer just passive storage systems. They are active, intelligent components that shape how we interact with technology and how businesses operate. Understanding MongoDB and the broader NoSQL movement is not just about learning a technology. It's about grasping a fundamental shift in how applications are built and how data truly drives value. You now possess a foundational understanding of why MongoDB exists, how it works, what it's good at, and how it's being used to solve complex real-world problems. This knowledge empowers you to make more informed decisions, whether you're a business leader strategizing digital transformation, a developer embarking on a new project, or simply a curious individual trying to make sense of the digital world around you. The best way to truly internalize this knowledge is to get hands-on. Theory is valuable, but practice brings understanding. 10.5 Further reading resources. To continue your journey and deepen your understanding of MongoDB, consider these conceptual next steps. Official MongoDB documentation, the most comprehensive and up-to-date source for all things MongoDB. It contains detailed explanations, tutorials, and reference materials. MongoDB University offers free, self-paced online courses covering various aspects of MongoDB, from fundamentals to advanced administration and development topics. It's an excellent way to gain practical skills. MongoDB Atlas Free Tier. Get hands-on experience without setting up a server yourself. MongoDB Atlas offers a free tier that allows you to deploy a fully managed MongoDB cluster and experiment with your own applications. Community forums and online groups. Join the vibrant MongoDB community. Engaging with other users and experts is a great way to ask questions, share knowledge, and stay abreast of new developments. Specialized books and tutorials. For deeper dives into specific topics such as advanced aggregation, specific use cases, e.g., geospatial applications, or performance tuning, explore more specialized technical books and online tutorials. The world of data is constantly evolving, and so is MongoDB. By continuously learning and exploring, you'll be well equipped to navigate the future of data in our increasingly connected world.